Welcome to Lecture 9 on Power Series. We're in Section 11.9 of our text, which is Stewart Calculus. Um, we, if you are just tuning into this, realize that this is made for my Calc 2 students, and it assumes a certain background in mathematics. So if you haven't studied Calc 2 or part of Calc 2 before, you might have a hard time following this, but you're welcome to try. So last video we had pointed out that we can integrate and differentiate power series term by term, and we can use that to try and find power series expansions for functions that aren't directly geometric series. So the examples we had last time is functions that were derivatives of functions that were geometric series, and this example we're going to actually look at just the opposite. Now ln of 1 plus x here. Let me just point out that that in fact is a constant plus the integral of dx over 1 plus x, right? Because the integral of dx over 1 plus x, if you do use substitutions, ln 1 plus x. So this is really an ideal situation. Once you recognize this, you can say this is the integral of this power series, because 1 plus x is the power series, negative x to the n, which is negative 1 to the n, x to the n. And of course that series, that's plus there. That series expansion is true if negative x is less than 1, the absolute value, that's negative 1 less than x less than 1. So once we recognize this as the integral of 1 over 1 plus x, then knowing that we have the power series expansion of 1 over 1 plus x, we can then write that as a power series. And the big theorem last time was that we can differentiate that, we can integrate that term by term. So it's going to be the sum of what we get as the integrals. Well, negative 1 to the n is just a constant. So I get x to the n plus 1 over over n plus 1. And of course now we can solve for c by plugging in the appropriate values of x. So let's just try, if x equals 0, ln of 1 plus 0 is equal to ln of 1, which equals 0, right? So the left-hand side will be 0, and c plus n equals 0 to infinity of negative 1 to the n x to the n plus 1 over n plus 1. Well, if x is equal to 0, all of these terms in this series disappear, right? So I just get 0, c. So on the left-hand side I get 0, on the right-hand side I get c. Those are equal, so c is equal to 0. So this is going to be sum n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. And we can simplify that a little bit by writing it as the sum n equals 1 to infinity of negative 1 to the n plus n minus 1, x to the n over n. Now, the thing is that's going to be true as long as x is between negative 1 and 1. It may actually be true at negative 1 or 1. It has the same radius of convergence, not necessarily the same interval of convergence. So let's actually see if we can figure out what the interval of convergence is. We know it converges between negative 1 and 1. It converges when your x is big. It diverges when x is bigger than 1 or less than negative 1. But we've got to check and see what's happening at x equals 1 and negative 1. So let's say x equals negative 1. What do I have there? I've got the sum n equals 1 to infinity of negative 1 to the n minus 1 of negative 1 to the n over n, which is the sum n equals 1 to infinity of negative 1 to the 2n minus 1, right? Which is negative 1 to the 2n minus 1 is just negative 1, so that's just negative sum n equals 1 to infinity of 1 over n, which is just what? Well, that's the harmonic series that diverges. That diverges. So let's try the other one, x equals 1. That's going to be sum n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n, which is the alternating harmonic series that's going to converge by the alternating series test. So the interval of convergence, this is equal here. This holds if x is an element of negative 1's not included, but 1 is included. This is the interval for which that's equal. Okay, so let's go with this next one. So the next one, well, the thing is you want to recognize this as the integral of 1 over 1 plus x squared, right? That's plus. So plus a constant. And once you have that, well, that's the, what is 1 over 1 plus x squared? Well, 1 over 1 plus x squared is 1 over 1 minus negative x squared, right? Which is equal to sum n equals 0 to infinity of negative x squared to the n. This is if negative x squared is the absolute value of that's less than 1. So this is going to be sum n equals 0 to infinity of negative 1 to the n, x to the 2n, which is, that's if absolute value of negative x squared is less than 1 is the same thing as negative 1 less than x less than 1, right? This is less than 1, that's not 4. So this is equal to c plus the integral of sum n equals 0 to infinity of negative 1 to the n, x to the 2n, that whole thing dx. But of course we can integrate term by term, that's the whole point. So that's plus the sum n equals 0 to infinity of the integral of negative 1 to the n, x to the 2n dx. So we're summing up all those integrals, and of course we bring all the constants together, and that sum's going to be c plus sum n equals 1 to the 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Okay, so let's do some erasing here so we can figure out the actual interval of convergence. So this is true, this here, let's see, this here is true if negative x squared is less than 1, right? Which is the same as negative 1 less than x less than 1. So we know that this arctan of x is equal to this here, as long as x is between negative 1 and 1, and it's not equal if x is bigger than 1 or less than negative 1. However, we don't know what's happening at 1 and negative 1. But let's first figure out what c is. So to figure out what c is, we're going to try arctan of 0. On the one hand, that's 0, right? On the other hand, when I plug 0 into this, all of these terms here except for c is 0, so c is equal to 0. Arctan of 0 is 0. When I plug 0 into this side, the right-hand side, everything zeroes out except for the c, so c is equal to 0. So we can ignore the c. So let's figure out what's happening at the endpoints now. At x is equal to negative 1, we get the sum n equals 0 to infinity of negative 1 to the n, negative 1 to the 2n plus 1 over 2n plus 1. And the thing is 2n plus 1's always odd, so negative 1 to that's always negative. So that's negative sum n equals 0 to infinity of negative 1 to the n over 2n plus 1, which is an alternating series that go to 0. This converges by the alternating series test. And now at x equals 1, for some reason this is not lowering. So let's say at x equals 1, we have the series n equals 0 to infinity of negative 1 to the n over 2n plus 1, which also converges by the alternating series test. So arctan here, arctan of x is equal to this series here on the closed interval from negative 1 to 1, because it converges at both endpoints. Okay, that's a good place to stop.